Hello and welcome to 10 Minutes Economics. In this video we'll learn how we can use the Solow model to analyze the long-term development of an economy. Moreover, we calculate the capital stock, the income and consumption per capita in the steady state. We will then also see how a change in the savings rate impacts the economy. In the Solow model we have a few important ingredients. And one of the most important ingredients, that's our production function. This production function combines the production factors capital, like machines, and labor, for example the number of workers or the number of hours worked in the economy, to produce the output. Remember that in an economy, production and income, also demand, but we focus on the first two, production and income are both the GDP of this economy. So let's look at our production function that combines capital and labor to the output. And as a particular example, we use here the so-called Cobb-Douglas production function. This Cobb-Douglas production function, as an example, multiplies the amount of capital and labor that we use in the production process. And we take capital to the power alpha and labor to the power 1 minus alpha, where this exponent alpha is usually strictly between 0 and 1. This Cobb-Douglas production function is often used in exams and tests, but also has some properties that make it rather convenient to solve the Solow model. And the first property is constant returns to scale. The following property holds if we double all inputs at the same time. So for example, we use twice the amount of machines and twice the amount of workers, then we double the output in the economy. In contrast, the second important property, that's the positive but diminishing returns or marginal products of each individual factor. So while for constant returns to scale we multiplied both inputs at the same time by a given factor, now we check what happens if we hold one input constant, for example labor, and only increase one input, namely capital. So if we now hold the number of workers constant and increase the number of machines, the amount of capital that we use, then each additional unit of capital has a positive effect on our output, on our production Y. And this is called the positive marginal product of capital. If we increase the amount of capital that we use, we increase the output. However, this positive effect of additional capital on the output that we produce, that gets weaker and weaker and weaker the more capital we already have. Let's say we have a factory with 20 workers and 5 machines. And if we give these workers the 6th machine, then the output goes up by 10 units. This is the positive marginal product. But if we give them an additional machine, then the output maybe only goes up by 9. If we give them one more machine, the output maybe goes up by 8.5. So yes, we still have a positive marginal product of capital in this case, but this positive marginal product is diminishing, meaning if we add more and more capital holding labor constant, then the positive output effect of this additional capital gets weaker and weaker. With our Solow model, we want to analyze how the economy is developing in the long term. If, for example, we want to compare the quality of life in China with the quality of life in Switzerland, then of course it makes no sense to compare the entire production, the entire GDP in Switzerland with the entire production of China. Switzerland looks pretty bad, obviously, in that comparison. Instead, we should conduct our calculation in per capita figures to take into account that there are simply a lot more people living in China. And that's why we focus on the income per capita. You can already see here how I define the income per capita, namely the total income in the economy, our total GDP Y, divided by the number of people N. This obviously means we don't make a distinction between the labor input and the population itself here. Both are simply N. Furthermore, we also see a convention regarding the notation here, namely that we use lowercase letters for variables that describe per capita quantities. For example, here, right, our income per capita. In contrast, the absolute, meaning the aggregate quantities at the level of the entire economy, are given capital letters. Right, so capital Y is, for example, our entire income in the economy, our real GDP. Capital K is the entire capital stock in the economy, the number of machines. Now let's take a more detailed look at the income per capita lowercase y. If we don't want our total income uppercase y, but the income per capita, well, we just have to divide our total income by the number of people in the economy N. So if we do that, right, divide simply both sides of the equation by N, then, well, surprise, on the left hand side you have y over N, and on the right hand side you have divided by N here. And now we use a little trick. Instead of dividing by n to the power 1, we can also write in the numerator times n to the power minus 1. So this here is gone. And in the numerator, we now have n to the power minus 1. And now you have in the numerator n to the power 1 minus alpha times n to the power minus 1. So we can simply add the exponents. So we have here 1 and we have here minus 1, and these two cancel out. And we are left with n to the power minus alpha. We are almost done. So now we can use the same trick in the other direction. So instead of having n to the power minus alpha in the numerator, we can also write n to the power plus alpha in the denominator. Finally, if we now look at the right hand side, we now have k over n to the power alpha, and k over n, the total capital stock divided by the number of people, that's simply our capital per person, our capital per worker, and we use lowercase k for that. If we now look at our result, then we see that our income per capita on the left hand side only depends on the capital per capita, lowercase k, on the right hand side. So as soon as we know what happens to the capital per worker, we know what happens to the income per worker, and that was our ultimate goal. Let's have a quick look at this function that shows us the income per person that we actually care about. To differentiate this per capita income from the production function at the aggregate level, this per capita income is often called production function in intensive form. And this production function has the following properties that in the end come from the properties from the aggregate production function that we discussed before. On the horizontal axis, we have the amount of capital per person, and on the vertical axis, we have the income per person. And here I picked alpha equal to 0.5. In other words, in our case, the income per person is simply the square root of the capital per person. For example, if you have 100 units of capital per worker, then the square root of that is 10 units of income per person. So what happens now if the capital per person increases, so if we move to the right in this diagram? What does it actually mean if we increase the capital per person? In the end, capital per person means you're looking at one person, so in the end you kind of hold the amount of labor equal to 1 and just increase the amount of capital that this one person has. And now we remember the property of the positive but diminishing margin report of capital, meaning if we hold labor constant, here equal to 1, and increase the amount of capital, then we have a positive margin report of capital, meaning if you have more capital per person, then also the income per person goes up. But because of this diminishing margin report of capital, each additional unit of capital per worker has a weaker effect, a weaker positive effect on the income per person. Meaning, this production function in intensive form is increasing, but the slope is getting smaller and smaller, right? So it's getting flatter and flatter. While the production function is the first main ingredient of the Solow model, the second main ingredient tells us how the capital stock in the economy changes over time. Specifically, in every period in our economy, we invest into new capital, and this is our investments uppercase I. So don't think of financial investments. It's not buying shares or bonds. It's really firms investing into factories, machines, stuff like that. So these new investments, that's added to our capital stock, that's added to the number of machines that we have in the economy. In a closed economy, which we usually consider if we look at the standard Solow model, in such a closed economy where no capital can come from outside and without the government interfering, so there are no government expenditures, no taxes, stuff like that, the investment of the firm, so the demand for capital, must be equal to the supply of capital in the economy, and that's the savings. And in order to specify the savings a little bit more in detail, the Solow model assumes that the households save a fixed, meaning exogenous share S of their income. So for example, lowercase s equal to 0.2 would mean that the people save 20% of the income and spend 80% of their income. So let's put this together. If we know that the people save the fraction S of the income Y, then the total savings in the economy and therefore the total capital supply is equal to S times Y. So while these investments, that means our savings, increase the capital stock from period to period, a certain share of machines, that is to say a certain part of capital that we have, breaks down in the same period due to depreciation. Specifically, we say that the exogenous share delta of our machines, for example, delta equal to 0.2, would mean 20% of our machines breaks down and is lost due to wear and tear. Hence, we know that the depreciation of capital between this period and the next one is delta times the amount of capital that we have right now. So let's combine everything. If right now we have the capital stock KT, then our savings and therefore the investment S times Y will be added to it, and at the same time the amount delta times K of capital is depreciated. This means our current capital stock plus the new investment net of depreciation, this is going to be the capital stock in the next period t plus 1. We can rewrite this by simply dragging the KT from the right hand side to the left hand side, then obviously with a minus. And now we realize that on the left hand side we have the absolute change of our capital stock between this period and the next one. And this change in the number of machines between this and the next period, that's what we call a delta K. So this triangle, that's a capital Greek delta. And we always use this delta to indicate an absolute change. So in our case, delta K means how many machines have we added from this period to the next one. And in the end, what does this equation mean? The net investment, so the net change in capital between this and next period, is the difference between the gross investment, what we invest into new capital, net of the capital that has been destroyed by depreciation. While it's nice to know what happens to our aggregate capital stock K here, what we really care about is the evolution of the capital per person, because if we know what happens to lowercase k, then we know what happens to our income per person, and that's what we care about. If we want to know what happens to the capital per person, well, we divide by the number of people n here. So then here on the left hand side, we now have divided by n, and on the right hand side here, we also now have divided by n. So this means on the left hand side, we don't have the change of the aggregate capital stock anymore, but we have the change of our capital per worker, lowercase k. On the right hand side, here we divide our aggregate income by the number of people, and this gives us lowercase y, the income per person. And for the second term here, in a very similar way, we divide the total amount of capital by the number of people, and that gives us the capital per worker, lowercase k. One more step and then we are done. Here we have our income per person, lowercase y. We know our income per capita is our capital per capita to the power alpha. So if we substitute this here, we come to our main equation of the Solow model that shows us how the capital per worker changes over time. Right? Remember, S is our savings rate and Y is our income per person. So in the end, what we have here, S times K to the power alpha, that's our savings per person and therefore our investment into new capital per person. And we take away the depreciation per person, right? K is the capital that we have per person, and share delta of that is destroyed by wear and tear. Our main equation of the Solow model shows us how our capital per worker changes over time. And this change of the capital stock over time is composed of two effects, right? The green one that comes from the savings per person and the red one that comes from the depreciation per person. In this diagram that you can see below, we have split these two effects, the green savings and investment and the red depreciation, into two separate lines. On the horizontal axis, there's our capital per worker. And if we now want to know how our savings per capita, SK to power alpha, depend on the capital per worker, we have to remember that this green savings per worker is the savings rate that's given times our income. And we already discussed what our income per capita looks as function of the capital per capita, right? This was this blue production function in intensive form that we discussed before. So even though we don't directly need our blue production function to analyze these dynamics of the capital per worker, I still drew it because I know my green savings and investment per capita is simply this blue income per capita multiplied by S. So basically pushed down by the factor S here by 50%. So for example, here, when for whatever reason my income per person is 6, then my savings and investment per person is exactly half of that, namely 3. This of course also means that the green savings investment per capita has the same properties as the blue production function in intensive form, namely it's increasing in the capital per worker. So more capital per worker means more income and therefore also more savings and investment per worker. But this positive effect of more capital on the saving and investment per person is diminishing, meaning the slope is getting smaller and smaller, this curve is getting flatter and flatter. And in order to find my delta K, my change of the capital stock, I now have to subtract simply the depreciation. But depreciation is simply the share delta of the capital that I have right now. So for example, here I set delta equal to 10%. So graphically speaking, this is simply a straight line with the slope 0.1. So for example, if you have 60 units of capital, then 10% of that is depreciated, right? This would mean your depreciation would be 6. Also note that we draw this red depreciation in absolute terms. So in order to find our delta K, our change in the capital stock, we have to take the green line, our savings per capita, and subtract the red line, our depreciation per capita. And the difference between the green and the red line is our delta K. So this difference is telling us by how many units our capital is increasing or decreasing. Let's say, for example, we start with 16 units of capital per worker. Then with our production function, the income per worker is the square root of that. And the square root of 16 is 4. So our income per person is 4. Out of these 4 units of income per person, we save 50% of that, right? So we have to go to the green curve, and the green curve is showing us our savings per person are 2, and therefore also the investment per person is 2. But at the same time, we have a depreciation of 10% of the capital that we have right now. So if you still have these 16 units of capital at the moment, 10%, so 1.6 is depreciated. And the difference between both 2 units that we save and invest and the 1.6 units that are lost by depreciation, so the difference between the green and the red curve, which is 0.4 in our example, this is added to the capital stock. So the next period we would have 16.4 units of capital. And then we look again at the diagram and we see the green curve is still higher than the red line. So the savings investment per person still exceeds the depreciation, so our capital worker is still increasing. So that means we continue to move to the right until we reach this point. It's already labeled as steady state. And in this point, in our case with 25 units of capital per worker, if you have 25 units of capital per worker, your income is the square root of that, that's 5. And half of that you save, so your savings investment per capita is 2.5. And your depreciation, namely 10% of the 25 units of capital that we have right now, is also 2.5. So your investment into new capital in per worker terms is just enough to compensate for depreciation. So your capital neither increases nor decreases. And next period you again have 25 units of capital per worker. And this continues forever. So long story short, you converge to this point where the savings investment per person and the depreciation per person intersect, where both are equally large, and then you don't move any further. The same works from the other side. If for whatever reason your initial capital per worker exceeds this steady state level of capital per worker, we call this case star, then your depreciation is higher than the actual investment into new capital, so your capital shrinks, and once again you move here to the left until you reach the steady state. Fortunately, we can calculate the steady state very quickly, right? In our long run equilibrium, the per capita savings rate times income per person, have to be equal to the depreciation per capita. So now we simply have to solve this for the amount of capital where both lines meet. So first step, we divide both sides by k to power alpha. Then on the left hand side, it obviously disappears. And on the right hand side, I can either divide by k to power alpha, or I can multiply by k to power minus alpha. Remember that we want to isolate our capital stock. So in the next step, we divide both sides by delta. So here it disappears, and you have the delta here in the denominator. And because we're interested in the capital stock, we switch sides. So we flip the left and the right hand side. So now you have the k to power 1 minus alpha on the left and s over delta on the right. Now we're almost done, but of course we don't want k to power 1 minus alpha, but simply k. So how do we get rid of this to the power 1 minus alpha? Well, we take everything to power 1 over 1 minus alpha. So if you take the left hand side to the power 1 over 1 minus alpha, then you basically divide here this exponent, and you simply have k to power 1 on the left hand side. And on the right hand side, you simply copy the exponent. So this means you now have k, the amount of capital per worker in the steady state, is s over delta to the power, well, as we just said, 1 over 1 minus alpha. So this is the capital stock in the solar model in the steady state. This is the capital stock that you have in the intersection of the diagram. It's very important to understand that in the solar model, everything is driven by the capital stock. So once we know what happens to capital stock, so for example, what is the capital stock in a steady state, we can calculate anything else in a steady state. For example, our income is steady state, right? We already know that our income with our Copernicus production function is k to power alpha. So if we want to know what's our steady state income, we just have to take our steady state capital stock and have to take it through power alpha. So this is why now in the exponent you have the alpha here. And that's already it. That's our income in the long run, this economy. Finally, you also might argue, well, income is nice, but in the end what I care about is the share of the income that I can actually use for consumption. And now remember our big assumption for the solar model. Namely, we said that the people always consume the exogenous fraction S of their income. So if we know that people save the fraction S of their income, then we know that they consume the fraction 1 minus S of their income. So our steady state consumption per person is our steady state income per person that we just calculated this year, right? Times 1 minus S. If this video has helped you so far, you can help me a lot by giving me a like. And if you want that YouTube suggests more of my videos, if you have questions on economics, then you should also subscribe to the channel. As a final experiment, let's see how a change in the savings rate affects the economy in the short run and in the long run. We want to analyze this increase in the savings rate graphically. Specifically, we assume that the savings rate increases from 50%, as it is right now, to 60%. So how does our diagram change if we increase the savings rate to 60%? The change of the capital per worker is still the difference between the green savings investment per worker and the depreciation. But if we increase our savings rate S from 0.5 to 0.6, then our green savings and investment curve is now not going to be 50, but 60% of our blue income per person. So if we increase our savings rate to 60%, then the green savings investment curve is pushed upwards. By the way, there's a link in the description where you can come to this dynamic diagram that I just showed you. So if you want to try other parameters, if you want to play also with the rate of depreciation delta, for example, or if you want to change the alpha, you can just change these parameters and look at the diagram how the curves are affected. So in our case, our savings rate increased from 50 to 60%, which basically dragged the green curve upwards. So in the new steady state, we now have a higher capital stock. To be precise, the old steady state increased from 25 units of capital per worker to 36 units of capital per worker. If you plug in these parameters that you see here into the equations from the slide we had before, then you get exactly these numbers. Right, and with 36 units of capital per worker, you have squared of that 6 units of income per worker. So during transition, starting from 25 units of capital per worker to the new steady state with 36 units of capital per worker, the income increases from 5 to 6. So during the transition from the old to new steady state, you do have some growth in capital and income per worker. But once you reach this new steady state, then the capital per worker and therefore also the income per worker is constant again. You also see this in our equations, right? If the savings rate goes up, then our capital per worker in the steady state goes up. Same is the case for our income per worker. However, if you look at consumption, then it's actually not that obvious, because if you have a higher savings rate, then in the steady state you will have more capital and more income. But if you have increased your savings rate, it obviously means that out of the now higher income, you save a higher fraction and therefore you consume a lower fraction. So while we know for sure if the savings rate goes up that you have more capital and income per person in the long run, whether you can actually consume more in per capita terms depends on which effect is stronger, the positive effect on the income or the fact that you now save a higher and therefore consume a lower fraction of that income. Of course, there is a way to find out which savings rate would maximize our long run consumption. We can use the so-called golden rule for that. But I think for today that's enough. So I'm going to make a new video on the golden rule, and that's also going to discuss the effect of population growth. If you have questions or suggestions for other videos on topics in micro or macroeconomics, please leave me a comment. Furthermore, in the description box you can also find a link where you can download these slides here. There's no registration, nothing. It's simply a link that you click and then you download the PDF. Finally, I also created another PDF with a numerical example, which you can also download below. All right, that's it. In any case, good luck with your studies and see you next time.